In this video, I'll be showing how we can derive the component definition of the cross product. And I'm going to do that by multiplying two vectors together symbolically. So I've got these two vectors here, and I've done the first step already where I've multiplied out each term. So I've got for example, this term, I'm taking the first two terms, pulling the components out front, and then we're taking the cross product of the unit vectors for each term. So what we're going to do is we're going to simplify this equation here, and I'll start by drawing out our coordinate system. So if we have three dimensions here, with our x direction, y direction, and z direction, what we can do is think about the relationships of these three directions in terms of the properties of our cross product. So to do that, we can look at the properties of the sine function. And we remember that when theta is 0, sine of theta is also 0, which means that the cross product between the two vectors is 0. So what this is essentially saying is if we look at our coordinate system, if you have the cross product of vectors in the same direction, then the cross product is 0. So that means if we look at our equation, any terms that have the same number, the same unit vector is 0. So we can immediately reduce it by crossing out these terms as 0. And so in words, I cross I equals j cross j equals k cross k equals 0. Okay, now the other thing is we talked about in the last video that cross products are anti-commutative. So for example, I cross j is equal to negative j cross I. And so we can come up with relations like this. Now, another thing to note is if we use our right-hand rule, let's think about this for a sec. I cross j, so if we're going from I to j, like this, and we use our right-hand rule, we're curling our fingers this way, and our thumb is now pointing in the k direction. So that means that I cross j is just k. Now, we can build out the same relations for each direction. So let's look at, if you use your right-hand rule for the rest of the directions, you'll get that j cross k is equal to negative k cross j, which is equal to I. And then k cross I is equal to negative I cross k equals j. And so these are kind of the four equations, if you like, that we can use to reduce this. Of course, if you put the negative here, if you take the negative of these, then you get negative k, negative I, negative j. Okay, so how can we use this to reduce this equation? Well, what we're going to do is look at terms like this, where we have I cross j, and then look at terms where we have j cross I. What we can do is, basically, I'm going to take the equations and reduce it or change the terms to everything that's on this side. So j cross I will flip to I cross j. K cross j, I'll flip to j cross k, and so forth. And so that's what I'm going to do. You could also do it the other way. It doesn't matter as long as you have terms that are the same, and then we can group them together. So I cross j is on the left side here, so I'm going to leave it the same. And then I cross k is on this side, so we want to flip it, and then we have to change the sign because it's anti-commutative. So I'm going to say this is negative ax BZ K cross I. J cross I, same thing. We subtract AY BX. We turn that to I cross J. So now we have two of the same terms here. Then this term 0, so J cross K is on the left, so that stays the same. K cross I is the same. K cross J is on this side, so we flip it, change the sign. And then that's J cross K. Okay, now we can group the like terms. So we have two terms that are similar, have the same unit vector configuration. So I'm going to take this term here. So AXBY, and then find the other I cross J term, this one. So that's minus AYBX. So I'm pulling the components out front, and then we'd have I cross J here. But let's reduce it further, because we have this final relation here where I cross J is equal to K. So we can simply just write K instead of I cross J. Now, let's do the other terms. So we have this one, negative AX BZ, K cross I, and I'm going to take the positive one first, just to make it look nicer. AZBX minus AXBZ, J cross I, so that's, or K cross I, excuse me, that's J. And then finally we have our last term, which is J cross K. So we have plus AYBZ minus AZBY. That's K. And so this is our cross product. So notice it's a vector, which is what we expect. And, sorry, this should be I here at the end. But that is our vector. This is our cross product vector. Now the components here, this is our Z component. This is our Y component. And this is our X component. So if you want to find your cross product vector, this is how you do it. You take your components of your individual vectors and you write them in this form. And notice that, for example, with the Z component, we don't have any Z component of A or B in here. The Z component of the cross product vector is in terms of the X and Y component of A and B. Same with the Y component. There's no Y component in here. It's in terms of the Z and the X component. So that is the component definition of the cross product, and we will talk about how we can calculate those in following videos. Thanks for watching.